Approach United 237 is 18.5, descending via the Eagle 6 with Sierra.
United 237 approach, expect division approach to runway 8.
Roger.
This lesson will be a series of 6 combined lessons where we will be teaching you about the 6 basic flight instruments in the Cessna 172 aircraft. These are the airspeed indicator, attitude indicator or artificial horizon, altimeter, turn coordinator, heading indicator, and vertical speed indicator. We will be discussing what these gauges represent and how they function. We will start with the airspeed indicator, or ASI. The airspeed indicator is used to tell the pilot what speed the aircraft is moving through the air. The airspeed indicator gives the pilot a speed reading in knots and TAS, also known as true airspeed. It is important to note that before flight, the true airspeed must be set. This is done by the pilot turning the true airspeed adjustment knob and matching the outside air temperature with the temperature scale on the airspeed indicator. For example, if the outside air temperature on the ground is 15 degrees Celsius, then the pilot adjusts the temperature scale on the airspeed indicator until the temperature scale is set to 15 degrees Celsius. Adjusting the temperature scale directly adjusts the true airspeed figures as well, so the speed readings will be correctly adjusted for the temperature of the day. The airspeed indicator calculates the airspeed of the aircraft by using pitot air pressure and static air pressure, or ambient pressure. The ASI then converts this pressure difference into an airspeed indication. Following on from this, we will now discuss the associated speed markings and the various color bands around the circumference of the instrument. The airspeed indicator incorporates a series of speed markers at 5-knot increments and 10-knot increments from 40 knots all the way up to 200 knots. The knot is the standard measurement of speed used within aviation. 1 knot is equivalent to 1.15 miles per hour. Therefore, if the aircraft is traveling at 100 knots, this would mean it would be traveling at the equivalent of 115 miles per hour. Moving on to the individual color bands, the white band on the indicator represents the flap operating range. The lower limit on this band represents VSO, which is the stall speed when the aircraft is in landing configuration, which in the Cessna 172 is when the flaps are fully extended. The upper limit of the white arc represents the maximum speed the aircraft can operate with flaps extended, or VFE. Moving to the green arc, the lower limit represents the stall speed known as VS1. In this instance, this is the stall speed of the aircraft when it is in its clean configuration with flaps fully retracted. This upper limit of the green arc represents VNO, or maximum structural cruising speed. Moving on again to the yellow arc, this represents a speed range to be flown in smooth air only. However, due to the rarity of this environmental condition, this represents an airspeed range to be avoided. The final speed representation to be aware of is the red line placed at the never exceed speed, or VNE. If the aircraft was to be flown above this speed, then structural damage could occur. We will now move on to the attitude indicator, or artificial horizon, in the Cessna 172. We will start by showing you what this instrument gauge represents. The attitude indicator gives the pilot a visual representation of what the aircraft is doing in relation to the horizon. For example, when the aircraft banks in relation to the horizon, this is how it is represented on the instrument. And when the aircraft pitches in relation to the horizon, this is how it is represented on the instrument. Now we will be showing you what each part of the instrument means and what it represents. We will start with the miniature aircraft symbol. This represents the wings and the nose of the aircraft and what they are doing in relation to the horizon. Then we have the artificial horizon line, which is indicated on the instrument in the form of this central horizontal white line, which separates the upper blue portion, which represents the sky, and the brown portion, which represents the ground. Moving on, the instrument has a variety of scale markings. We will start with the markings around the circumference of the top portion of the instrument. These scales represent bank angle. You can quickly determine what bank angle the aircraft is experiencing when the orange bug rotates over that designated bank angle line. The angles that are represented on the instrument are as follows. These are 0 degrees, meaning the aircraft is straight and level. Then, banking to 10 degrees, 20 degrees, 30 degrees, 60 degrees, and 90 degrees of bank. Moving on to the pitch of the aircraft, this is represented by the various horizontal black and white lines on the center portion of the instrument. The black lines on the blue portion represent a positive angle of pitch in relation to the horizon, whereas the white lines on the brown portion represent a negative angle of pitch in relation to the horizon. You can quickly determine what angle the aircraft is pitching to by aligning this particular circular point of the indicator, which represents the nose of the aircraft, with each of the lines that represent different degrees of pitch. The pitch angles that are represented on this instrument are as follows. They are 5 degrees and 10 degrees of a positive pitch angle, and 5 degrees, 10 degrees, and 15 degrees of a negative pitch angle. Another feature of this particular attitude indicator or artificial horizon is the adjustment knob. This knob, when turned clockwise, causes the miniature aircraft on the gauge to rise in relation to the horizon line. Subsequently, when the knob is turned anti-clockwise, the miniature aircraft drops in relation to the horizon line. This feature is to aid against parallax error. Parallax error is when a person's point of view is causing the pointer of a device to look like it's giving a different reading to what it would do when viewed square on. This is typically caused by height differences from person to person. For example, a shorter person will have a different point of view than a taller person. So when entering the cockpit, a taller person may have to adjust the knob to increase the height of the miniature aircraft, so from his or her point of view, the miniature aircraft now appears level to the artificial horizon line, whereas a shorter person may have to adjust the knob to lower the miniature aircraft so that it now aligns with the artificial horizon line. This instrument also includes an off flag, which comes into view when the internal gyro spin speed is too low. When in view, this indicates that the displayed information could be incorrect and should not be used. We will now move on to the altimeter. The type of instrument fitted to the Cessna 172 is a barometrically corrected altimeter. The altimeter provides the pilot with a reference for what altitude the aircraft is flying in relation to the ground. The altitude of an aircraft can be expressed in either feet or meters, however most barometrically corrected altimeters are calibrated in feet. Moving on to the various height scales on the instrument, the small white lines around the circumference of the instrument represent increments of 20 feet, and the larger lines indicate increments of 100 feet. Being able to correctly represent what altitude is visually represented on this instrument is crucial to a pilot. So, we are going to briefly walk you through how to read specific altitudes on this analog altimeter instrument. For example, how would a pilot know when the instrument is reading an altitude of 1,000 feet? Well, this is when the 100 feet pointer makes a 360-degree movement around the entire instrument, and you will notice that in doing so, the 1,000 feet pointer is now pointing to the number 1 on the instrument, which tells the pilot the aircraft is at exactly 1,000 feet above the ground. For altitudes of 10,000 feet and 20,000 feet, this can be quickly identified by the 10,000 feet pointer, pointing to either the number 1 on the instrument, which shows the aircraft is at 10,000 feet, or at the number 2 on the instrument, which shows that the aircraft is at 20,000 feet. Moving on, we will now discuss how the altimeter works. The altimeter we are referring to in today's lesson utilizes the aircraft's static pressure or atmospheric pressure. The altimeter uses the difference in static pressure when the aircraft is climbing from what it was when the aircraft was on the ground, then it converts this pressure difference into an altitude reading for the pilot. It is important to note that before flight, the altimeter barometric pressure must be set, so the instrument gives the pilot an accurate ground altitude reading. This is carried out by contacting the departure airport's air traffic control or by listening to the departure airport's ATIS or Automatic Terminal Information Service, which gives the pilot the local pressure setting of which to correctly set their altimeter to before flight. In order to adjust the instrument to show this pressure reading, the pilot must adjust the knob on the instrument, which in turn adjusts the pressure scales within the instrument, and when set to the pressure reading given to the pilot by listening to the departure airport's ATIS, will provide the pilot with an accurate ground altitude reading for the departure airport. It is important to note that this pressure will have to be adjusted throughout the flight, especially if traveling to destinations that are of a different height above sea level to the departure airport. The reason for this is because the pressure decreases by 1 inch of mercury per every 1,000 feet of altitude increase. So for instance, if you are departing Schiphol Airport in the Netherlands, which is 12 feet below sea level, and traveling to Zurich in Switzerland, which is 1,390 feet above sea level, without adjusting your aircrafts altimeter pressure, your altitude would be wrong by the difference in sea level elevations between the two airports, which in this case would be 1,402 feet. We will now move on to the heading indicator. The heading indicator gives the pilot a heading reference that the aircraft is flying in relation to the magnetic North Pole. We will now go over each of the individual parts of the heading indicator's display and explain what they represent to the pilot. We will start with the compass rose, which as you can see is made up of a series of scale markings in differing lengths. The short lines on the instrument represent increments of 5 degrees, and the long lines represent increments of 10 degrees. There are also letters and numbers on the rose, which indicate specific headings. The main cardinal points on this compass, such as north, east, south, and west, are represented by the first letter of their corresponding point. For example, north is represented by the letter N, east is represented by the letter E, and so on. We will now explain what each of the numbers and letters represent in terms of their heading degree. Starting with the cardinal points, north represents an angle of 360 degrees, east represents an angle of 90 degrees, south represents an angle of 180 degrees, and west represents an angle of 270 degrees. The individual numbers on the rows also indicate their own corresponding heading degree. Quite intuitively, the exact degree the number represents is shown on the instrument, however it is simply omitting the 0 at the end of the number. For example, the number 3 on the rows indicates an angle of 030 degrees, 15 indicates 150 degrees, and the number 30 represents 300 degrees, and so on. The heading indicator also includes relative heading markings. These are set at 45 degrees, 90 degrees, 135 degrees, and 180 degrees, relative to the aircraft's current heading. These are present on the instrument, so the pilot can quickly determine what either 45, 90, 135, or 180 degrees is from the current aircraft heading. This is important, as in some instances, air traffic control will instruct a pilot to turn to an exact angle from their current heading. For example, if you are flying west at 270 degrees and air traffic control instructs you to turn 45 degrees to the right, you can quickly determine what heading you need to turn to by looking at the relative heading marking at 45 degrees to the right, which will tell you that you need to turn to a heading of 315 degrees. Moving on, the indicator also has a heading bug. This bug can be rotated by the pilot so that he or she has a visual reference to what angle they need to turn to when instructed by air traffic control. For example, if you are flying at a heading of 360 degrees and air traffic control instructs you to turn to a heading of 055, you can simply turn the heading knob on the instrument that turns the heading bug, then align the bug to 055 degrees on the compass rose, and then you will have a visual reference for where to turn to. This bug also works in conjunction with the autopilot system, but you can use it for either manual or automated flight via the autopilot system. Finally, the instrument also incorporates a miniature aircraft symbol. This provides the pilot with a visual representation of where the aircraft is heading, when the point of the miniature aircraft symbol points to one of the heading degrees on the compass rose. As you can see in this example, the point of the aircraft symbol is pointing to the letter N, which means the aircraft is heading 360 degrees. It is important to note that this heading indicator instrument suffers from an effect called wander, specifically apparent wander. This particular effect we will discuss in greater detail in another video. However, what it basically means to a pilot is that over time the heading indicator instrument will start giving the pilot an incorrect reading by deviating by several degrees from its original setting over the course of 10 to 15 minutes. So to combat this, the pilot should compare the reading on the heading indicator to the reading on the magnetic compass, which is situated on the glare shield of a Cessna 172 aircraft, and if required, adjust the heading indicator to match the heading reading on this compass instead, since the magnetic compass doesn't get affected by this type of wander. However, this adjustment should only be made when the aircraft is flying straight and level and at a constant speed, as this will be the only time the magnetic compass will indicate the heading correctly. We will now move on to the vertical speed indicator. We will start by showing you what the vertical speed indicator represents to the pilot. The vertical speed indicator represents either the rate of which the aircraft is climbing or the rate of which the aircraft is descending to the pilot. In order to quickly tell which is happening to the aircraft, imagine that the instrument is split in half horizontally, so all the scales in the top portion of the instrument, which we have highlighted in blue, represents a rate of climb, and all the scales in the bottom half portion of the instrument, which we have highlighted in brown, represents a rate of descent. You will also notice that the instrument actually states this by means of having up written by the blue arrow pointing in an upward direction and down written by the brown arrow, which is pointing in a downward direction. So the instrument is quite intuitive in this way. We will now move on to the individual scale markings on the display of this instrument and show you what they represent. You will see that in both the climb and descent portions, there are identical scale markings with numbers next to them. These scales represent an exact rate of either climb or descent, which are measured in hundreds of feet per minute. As well as these scales, there is an indication pointer that will rotate over these scales to indicate the exact rate of either climb or descent to the pilot. So, for example, if the pointer is pointing to the number 5 in the upper portion of the instrument, this would indicate that the aircraft is climbing by 500 feet per minute. Alternatively, when the pointer is pointing to the number 5 on the bottom portion of this instrument, this would mean that the aircraft is descending by 500 feet per minute. You will also see that in between 0 and 10 on either portion of the instrument, there are smaller white lines. These small lines indicate increments of 100 feet per minute, whereas the thicker lines with the numbers next to them indicate increments of 500 feet per minute. So, for example, if the pointer is pointing in this position, this means that the aircraft would be climbing by 300 feet per minute, because it is the third line away from 0, meaning that it represents 300 feet. Alternatively, if the pointer is pointing in this position, this means that the aircraft would be descending by 300 feet per minute. Moving on now to how the instrument works, the vertical speed indicator gets its information from the aircraft's static port, which is situated on the outside of the aircraft. You may ask, how does the instrument take static pressure and then convert that into either a climb or descent rate reading? Well, the instrument takes differences in static pressure, which is also known as atmospheric pressure, when the aircraft climbs or descends, and then converts that into a reading for the pilot. The instrument takes advantage of the fact that static pressure becomes less dense as the aircraft climbs, whereas when the aircraft descends, the static pressure is becoming denser. So, if the aircraft is in straight and level flight, the static pressure will remain constant, causing the vertical speed indicator to point to 0, indicating that the aircraft is neither climbing or descending. However, if the aircraft were to climb, the static pressure would decrease. This would in turn cause the instrument to give a reading to the pilot that the aircraft is climbing. The opposite is true for when the aircraft is descending, because as the aircraft decreases in altitude, the static pressure increases. The instrument then takes the differences in static pressure and converts this into a descent reading on the instrument. So in basic terms, the way the vertical speed indicator operates is by interpreting the differences in static pressure as changes in altitude, and by measuring how fast the pressure changes, it converts the speed of that pressure change into a rate of change of altitude reading for the pilot. That is the end of this lesson. We hope you found it useful for your studies. Thanks for watching, and please don't forget to subscribe as more videos will be coming very soon.